Hello, everyone. Hello, everyone. This is Dr. Vishal Sharma, who is principal at Metanoia Inc. and also owner and moderator of the Carrier Ethernet Group. And today I'm delighted to bring you another one of my network architecture and design series videos. And in particular, the question we're going to answer today is which scheduling mechanisms are implemented most often in switches and routers, and which are the ones that are most widely deployed by service providers. Now, as many of you know, my network architecture and design series videos are designed for, as you might imagine, network architects, principal architects, system architects, senior hardware and software engineers, working at chip companies, ASIC companies, system vendors, software providers, and of course at the operators themselves. And the goal of these videos is to discuss a short technical topic in some degree of depth to enable people to learn something about contemporary technology that they can then apply to their jobs. And the inspiration for these videos comes from my own work and interaction in the industry with my clients and my colleagues, and also from a number of different queries that keep coming up on the Carrier Ethernet group that I own and moderate. So this particular one was actually a question that was asked by Sham Naragun, a colleague of ours in the Carrier Ethernet group. And I would therefore like to acknowledge the following 8 members who were very, very helpful in taking the discussion forward on the group and contributed their thoughts and ideas and so forth. So what you're going to see in the video today is an amalgamation of many of their thoughts, as well as my own research, analysis, and thinking in trying to answer the questions that are the subtopics for the main question at hand. And so there are really 4 questions that I'm going to answer in this video. And those are, which scheduling mechanisms do operators most often deploy? Which scheduling mechanisms are most widely implemented in switches and routers? So these are 2 distinct things. On the one hand, we're looking at, okay, what is it that the operators most frequently deploy? And on the other, we are trying to understand what is it that is typically found in switches and routers of the day. And a related question is, as you might imagine, there are a whole slew of mechanisms that are available, and one might wonder, why are different mechanisms used in different parts of the network? And more importantly, at the end, when is scheduling even relevant to the kinds of networks that we are building today? So these are the 4 questions we'll answer, and we will build up to the pieces that will help us in answering these questions. In fact, we'll answer the actual question of operator deployment at the very end when we built up all of the other connecting bits. So let me stop my screen share right now and come back to you and talk to you about the actual question that led to this whole video being launched. And let me do another screen share to share with you what came up on the Carrier Ethernet group so that you all can also appreciate where we are going with it. So this is where the discussion on the Carrier Ethernet group came up. Sham brought it up just about a month back. And as you can see, there were 30 comments to this. So obviously a lot of discussion, a lot of interaction among the group members as we tried to sort these issues out. Now, this is the Carrier Ethernet group, as many of you know, is a collection of, as you can see here, almost 10,182 plus members at this point from well over 3,200 companies and over 139 nations across the globe. And it is focused on, as the name says, the technology, strategy, and business of modern packet networking. So we are discussing many things on 6 channels that are listed here, 7 in fact now, with the wireless being our latest addition. But let me not digress too far. Let's come back to the 4 basic questions that we are trying to answer in this workshop, in this video. And as I said, which scheduling mechanisms do operators most often use in their networks? Which mechanisms are most often implemented in switching and routing systems? And of course, why are different mechanisms used in different parts of the network? Of course, the assumption is that we understand that different parts of the network, namely access, edge or metro, and core, use different kinds of scheduling mechanisms, and we'll talk about that in a minute. And then finally, when is queuing and scheduling even relevant? So let's start with the mechanism. So in order to answer which mechanisms are most frequently used by the operators, we must understand that the mechanisms that are used depend on at least 3 factors. The first is the network segment that we are talking about, because the mechanisms differ between access, edge, metro, and core. And the second is the capabilities of the equipment that's deployed in the network. Uh, because really, the quality of service and the scheduling is very closely tied to the hardware capabilities of the boxes that are in the network. And therefore, you can only do what your hardware will allow you to do. So it's extremely imperative that the operators have a very good sense of what are the capabilities and limits of the different hardware devices that are deployed in the network. So there's a need not only to understand this at the architecture level of the data plane of the boxes that you deploy in the network, but also to understand that through testing in the lab. Because that's the way you can make sure that there's a fit between the wide range of applications you might want to run on the network and the hardware devices that are going to give you the ability to support quality of service for those apps. Now, in an ideal world, you would look at the hardware platform that would be chosen first. You'd look a few years out in the future. You'd look at, what are the applications and services you expect to deploy 3, 4, 5 years down the line, and pick your hardware based on that. So there'd be a good match between the hardware and what you expect to come down the line. In reality, it's quite the reverse, actually. The hardware is typically deployed. New applications are emerging as time goes on, and those are the ones that you then need to deploy on the hardware. And that's where knowing your hardware capabilities inside out kind of becomes important. Now, the third thing that the mechanisms that are used actually depend on is the applications that are running in the network. Are they real time, for example, voice and video? Are they non-real time? Just bulk data transfers, high reliability, internet transactions, and then what kind of services do you have in the network? Voice services, video services, gaming services, high priority, financial service transactions, and so on and so forth. Because the needs of these applications are different. And as such, you need different mechanisms to be implemented in different segments of the network. And this is because, as I said earlier, the capability of the boxes in different parts of the network is different because you cost and budget different network segments differently, and you buy boxes of different capacities and different capabilities for different parts of the network, like the access, the edge, and the core. And then the degree of aggregation of traffic also varies quite a bit between these segments. So for example, the access, you might think of having individual customer flows or individual applications, and you might want to shape based on those flows and applications. But as you start moving towards the edge, you may have per customer or per service aggregation or per application aggregation, and you may create larger bulk flows. And then when you get to the core, there's even a higher level of aggregation where you might aggregate per service, per region, per applications traveling across a certain part of your network, and a number of different criteria. So the granularity of the traffic and the granularity at which you need to give quality of service and scheduling comes as a part of that varies from different parts of the network as well. So before we can talk about what mechanisms are used where, I think it makes sense to talk about the different scheduling mechanisms that actually exist. And for that, I'm actually going to screen share with you some handwritten notes that I use typically to explain and understand things. So I'm going to move to my handwritten notes, plain and simple. And I'm going to list all the scheduling mechanisms. Now, I'm not going to describe in great detail the operation of each mechanism. That's a subject of a separate video that I'm actually a companion video to this one that I encourage you to watch, which talks about the operation of these schedulers. But what I will do is list the schedulers and illustrate for you kind of the differences between them. So there actually, it turns out, 7 different kinds of mechanisms that I've classified things into. The first is the FIFO, or the first in, first out buffer, where packets come in and packets go out. All the scheduler does is read the packet at the head of the queue, transmit it on the outgoing link, and that's pretty much all there is. Now, as you can imagine, in a FIFO, there can be all of the different types of traffic gets merged into the same stream. So obviously, you have no way to differentiate traffic that has different requirements. For example, voice and video and data would all end up in the same queue. Well, that's okay for low-end equipment or areas of the network where you don't really care much about traffic differentiation. Clearly, that doesn't work. So what you start to do in the next scheduling mechanism, which is round-robin scheduling, is you put traffic of different types into different queues. Ideally, you put traffic of different flows into different queues. So ABC could represent flows, or they might represent collection of flows that have some similarities, for example, voice traffic, video traffic, data traffic. And in the round-robin scheduler, all you do is you go round and round in a round-robin fashion across ABC, every round, and you read one packet, assuming the queue has a packet, from each queue, and you transmit it on the outgoing link. Now, as you can imagine, if you just did vanilla round robin, you could have some discrepancy between the amount of traffic that is going to go out on the output link from different queues. So if A consistently had 40 byte packets and B consistently had 1500 byte packets, clearly you'll send in each round a lot more data from B than you would send from QA. So to take care of that, you can modify round robin by introducing what are called weights, where the weights can help you dictate what fraction of the outgoing link capacity is dedicated to a particular queue. And so now you can not only give different weights to different queues, you can also disambiguate them based on the traffic type. So you might give a higher weight to, let's say, packets or traffic that is voice or video or real time. So you might give a lower weight to something that's like email or low priority traffic. The catch in weighted round robin and round robin is that the bandwidth and the weight are coupled. So the higher the weight, the higher the fraction of the outgoing link capacity you get, which may or may not correlate to the importance of the traffic, right? You could have very high priority small packet financial transactions that actually end up in a queue with a low weight, and there's not much you would be able to do about it. It would be difficult to disambiguate those. So to kind of take care of that, we go into the third kind of queuing mechanism, which is weighted fair queuing. And what weighted fair queuing is that it's really trying to approximate what's called generalized processor sharing, which is an ideal queuing discipline, where the assumption is that the queues are like essentially pipes, and the outgoing link is one big pipe, and a small amount of fluid from all of those pipes is going out in parallel on the outgoing link. So the way WFQ works in reality for discrete size packets is that you send packets, you compute the earliest finishing time of packets, assuming that you have an ideal, generalized process sharing scheduler running in the background, and then based on those finishing times, you actually transmit packets from the actual WFQ queues. Now, again, in the WFQ system, you would have a queue per flow if you were going to do the purist's view. So therefore, you have a variant of that clause called class-based WFQ, where you don't actually create a queue for every flow. You group like flows together into a queue, which is a class queue. For example, you may have a class for voice traffic, you may have a class for video traffic, a class for email or data traffic, a class for high priority financial transactions, and so forth. And then you schedule based on classes as opposed to scheduling on individual flows. So that's what we have in WFQ. Now, even in WFQ, your bandwidth and delay are kind of coupled, because the higher the bandwidth, the lower the delay you're going to experience, because you'll be served faster from the queue. The other problem with WFQ is that because it needs to compute this finishing time and then always sort the packets at the heads of various queues in the order of their finishing time, you need order of n computation, if n is the number of flows or queues that you have, to schedule a packet out on the outgoing link, which can add up for a large number of flows or large number of queues. So deficit round robin is a variant of, you can think of as a discrete variant of WFQ, where for every queue you have two parameters. You have a quantum which controls how much data you can send out, and you have a deficit counter which balances between different rounds. If you send out more data in one round, you get to send out a little bit less in the subsequent round. So on average, only one quantum's worth of data is sent out of each queue in each round, although there may be localized variations when you look at it over a small period of time. And as you can imagine, WDRR is nothing but a variant of DRR, where you give the queues different weights. So in essence, different quantum sizes. So as opposed to giving, let's say, every queue a 500 byte quantum, you might give queue A 1,000 bytes, queue B 500 bytes, and queue C 250 bytes. So in effect, the weights are 4, 2, and 1 for the three queues A, B, and C. The next queuing discipline is what's called priority queue or low latency queuing. And what this is essentially you have one high priority queue which is served with strict priority, and then you have a selection of other queues that are served using one of the many other scheduling techniques we just discussed. So The low priority queues are all served by a scheduler that can either operate in round robin mode, in weighted round robin mode, in WFQ mode, as a DRR scheduler, or as a weighted DRR scheduler. And the higher level scheduler always picks packets from the high priority or priority queue, or also called a low latency queue, as long as there are packets to be sent. And once this queue is empty, it moves on to serving the other queues, which are in turn scheduled using one of these other kinds of schedulers. Now, the only difference between a priority queue and a low latency queue is that, as you can see, if you only had a priority queue and every time there was a packet in there, you served it, there's a potential that the lower priority queues could get completely starved. So if my priority queue was constantly occupied, I'd keep going back at the highest level and serving that with the strict priority. So to avoid that, in a low latency queue, what has been done is that you are allowed to send a certain amount of data from that queue, or you're allowed to use a certain fraction of the outgoing link bandwidth. And once you reach that, you can no longer be served, and the scheduler at the highest level goes on to serving the other low priority queues, which in turn are served using one of the other many types of schedulers. And a specific case of where you have a priority queue and the scheduler at the second level happens to be a DRR scheduler is known as a modified DRR or MDRR scheduler. So an MDRR scheduler is nothing but a priority queue or a low latency queue together with a DRR scheduler, which is the one we showed here. The next type of queue I want to talk about is what's called a prioritized weighted fair queuing system. And what this has is, this has a selection of queues which are ordered by priority. As you can see, priority 1, priority 2, 3, and 4. And within each priority level, the queues are served using weighted fair queuing, or one of the many variants that I talked about earlier. So you go in strict priority order, from priority 1 through priority n, and at any given priority, you serve the various queues at that priority using a scheduler, which is a weighted fair queue or a variant thereof. And finally, there's something called hierarchical QoS. So if you notice, in all of the schedulers that we've looked at so far, you typically have a single level scheduler. You have a bunch of queues, and you have a single scheduler, which can be like a one level scheduler. When you go to priority queue, you kind of had two schedulers, but if you think about it, it's really only one thing. You either are serving packets from this queue, or you're serving packets from these other queues at lower priority using some variant of weighted fair queuing or weighted round robin or round robin scheduling. So it's really all at the same level. But when you get to hierarchical queuing, you have schedulers at different levels. So at the highest level, you may have a 0th level scheduler which portions out the bandwidth of this outgoing link in some proportion to these other level 1 schedulers. The level 1 schedulers in turn portion out that bandwidth in some proportion again to the level 2 schedulers. And the level 2 schedulers, upon receiving the quantity of bandwidth that they can use, then apportion that appropriately between the actual physical queues of voice, video, and data, for example, using one of the many scheduling mechanisms that we've already talked about, one of the 4 or 5 mechanisms we talked about earlier. And so this hierarchical QoS is actually very beneficial when you have multiple levels of aggregation. So for example, you could have customer voice, video, and data traffic aggregated into customer level VLANs, and then the customer level VLANs are then aggregated into a provider level SVLAN, and that provider level SVLANs are then aggregated onto an outgoing link. So you can have multiple levels of scheduling that way. So these are different kinds of schedulers that exist. And just to recap, there are actually 7 types that I've listed out here. One is the plain FIFO, then round robin or weighted round robin, where you're just serving the queues in a round robin order. In weighted round robin, you have weights assigned, so you serve a certain number of packets from each queue depending on the weight. Since these can be unfair, you have WFQ, which tries to basically emulate a perfect queuing system, which is the generalized process sharing, and it does so by computing an earliest finishing time and then serving packets from the queues with the lowest finishing time. A variant of that is DRR WDRR, which tries to make sure that the packet lengths don't affect the fairness of the queuing, and so it allows in every round only a certain number of bytes to go out from each queue. which are adjusted over different rounds by a deficit counter, which accounts for whether extra stuff was sent out in a previous round, because you can only send whole packets. So if there is room to send a packet, you might end up sending a little bit more than the quantum, or in some cases a little bit less. And then you have priority queue, where basically you have one strict priority queue and then several other low priority queues that are served using one of the other schedulers we discussed. And then priority WF queue, where you have a collection of queues at different priorities, and at each priority, the subset of queues that happens to be at the same priority is served using WFQ or a variant. And finally, you have hierarchical queuing, where you have schedulers at different levels of the hierarchy, which are very good when you want to aggregate multiple entities at multiple levels. For example, voice video traffic from the customer into customer VLANs, and then customer VLANs into operator VLANs, and operator VLANs into actual network links. So those are the different types of scheduling mechanisms. And I wanted to point out that, let me stop the screen share and point out to you that in addition to all these different kinds of queues that we just talked about, which are primarily for data traffic, there is always in modern routers and switches a special high priority queue that's kind of hidden from this main set of queues for control traffic. So it can be for routing protocol packets, for keep alive, for BFD packets, for shortest spanning tree protocol packets, and so on and so forth. And that's not counted in these queues, because that is always a high priority queue with a small volume of control traffic that's always scheduled on every outgoing link before anything else is. So given this whole gamut of scheduling algorithms, let's answer one of the questions that we were talking about, which is which scheduling mechanisms are most widely implemented in the switches and routers. And I've actually done a mind map to give you all a flavor of what the different vendors are doing. Let me actually do a screen share and show you that mind map and walk you through some of its capabilities. And I'm going to show that, make that available as part of the video. You'll find the link in the description of the video. So as you can see here, guys, in this mind map, I've put together several things. I've given you a pointer to the original discussion right here. I've given you some references to different kinds of schedulers that I could find. Now, again, I want to point out that scheduling is a subject of at least 30 years of research. And there's a whole bunch of papers on it, not all of which it's possible to list here. So what I've given you is a flavor of the different kinds of things you need to know about. And then, of course, one can always go and do deeper research into that. And then I've given you some Wikipedia pointers to the basic scheduling disciplines for you to help understand that. A good way to understand it is my companion video, which talks in detail about the operation of these different schedulers. And then finally, I've given you some links to pages from the vendor implementations to give you a flavor for what kind of schedulers Cisco, Juniper, Alcatel, and Brocade and other vendors are using for what kinds of equipment. But at the end of it, when I look at all of the different options and I try to summarize it, here's what I can tell you. So the most common implementation for data traffic in the majority of the system vendors that we have looked at is basically some kind of a priority queue, coupled with some variant of either deficit round robin, because that's a computationally efficient algorithm. It works every round in order of one time as opposed to order of n times that you would need for WFQ, so it's simpler. Or there is some variant of WFQ itself that is used. Now, that depends on whether your switch or router is an access guy, which is a low capacity device and therefore not that advanced in its capabilities, or it's a core router which has access to a lot of hardware and high-end computation engines and can therefore do much more complex WFQ. So if the device is a metro or edge device or a core router, it typically has the ability, in addition to this strict priority coupled with DRR or WFQ, the ability to do maybe between 2 and 4 levels of hierarchical queuing that I explained to you earlier. And that allows for different kinds of aggregation of traffic into larger and larger streams. For example, MPLS tunnels, provider VLANs, and so forth. And it allows you to regulate at the granularity of that entity, a larger entity, or at the granularity of smaller entities, depending on what level you wish to go to. So that's about the scheduling mechanism. The next question is, which mechanisms are implemented or deployed in different parts of the network and why. Now, we talked about the why earlier. Different mechanisms are implemented in different parts because in the access network, you have a number of individual flows. But, for example, voice, video, and data from a given specific customer, but the number of flows is typically small, and there are small number per system, so you can manage with sort of low-end systems, but that will implement something like priority queuing and low latency queuing combined with class-based weighted fair queuing. When you move to the edge of the network, there are edge metro systems that are aggregating individual customer flows into provider flows. And so they may aggregate into MPLS tunnels or SVLANs or provider VLANs, and they will typically use, oh, I'm sorry, let me go back and actually share with you a table that I had built illustrating all of these so that it's a lot easier for me to walk you through that. So here's the table I wanted to share with you. Just one second. There you go. So in the access, so this table basically lists out the kind of schedulers that are most commonly deployed in different parts of the network. So if you look at the access, you typically have a priority queue or a low latency queue combined with weighted fair queuing or weighted round robin. Now, weighted fair queuing can be done in the access because you have a small number of flows. And so even though it's somewhat complex, you can still handle it. In particular, if you have a multi-tenant customer premise equipment, you can actually do priority queuing combined with weighted fair queuing at the intra Ethernet virtual circuit level. So a given Ethernet virtual circuit, presumably for traffic coming from a given customer, you can do priority queuing for, let's say, voice traffic or real-time traffic, and then weighted fair queuing among 2 or 3 other classes of traffic. At the inter-EVC level, you can just probably do weighted fair queuing because you've already scheduled specific application level data from a customer into a given EVC. And then it's a matter of just scheduling multiple EVCs out onto the output link of the CPE, and that can be done in a WFQ fashion. So that's what is most common scheduler that might be deployed in the access segment. By the time you come to the edge or metro segment, you can again do priority queue or low latency queuing with class-based weighted fair queuing, where you reduce the granularity with which you are keeping track of the different flows. Or you may do what's called prioritized WFQ, as I explained earlier. Or even more simply, you might do modified DRR with a low latency queue in the strict priority so that it doesn't completely dominate all of the outgoing link capacity. And finally, when you come to the core, you can do strict priority with modified DRR, or you can have 2 to 4 levels of hierarchical scheduling, where at each level, the scheduler could be one of the many schedulers that we've discussed of earlier. So these are the most commonly implemented mechanisms in these 3 network segments. And as you can see, they differ widely based on the requirements of the network segment and the kind of applications that we are using there. And so finally, the last question we want to answer is, when is queuing even relevant? And if you think about it, queuing algorithms and scheduling is only relevant if the service provider is offering an SLA where either latency or delay variation is at issue. Okay, because if you have latency and delay variation of different classes of traffic, and that's built into your SLA, you absolutely need to schedule to make sure that different classes of traffic are actually meeting their required SLAs. However, if the SLA is only based on, let's say, frame loss or on the availability metric, then frankly, it doesn't quite matter what queuing discipline you use, because you're not really basing your SLAs on drop packets. You're basing them on how many packets are eventually delivered to the endpoint, and you're not really worrying about either delay or bandwidth in the delivery of those packets. So if performance monitoring and SLAs are not critical, then the service providers can really use any default scheduling that's coming with the switching device without really having to worry too much about it. So there you have it, folks. There were 4 questions we started out with, and I think we have answered them all. At this point, if there are any other questions, I welcome you to use the links at the bottom of this video in the description and write directly to me, or go back to the Carrier Ethernet group if you're a member or if you want to become one, and of course comment on the very active discussions in the group, including the one on the schedulers. So thank you very much again. I appreciate your time, And I will look forward to seeing you next time. Until then, keep learning, keep advancing, and keep contributing. See you next time. Bye bye.